We introduced the transient well equation and then went through the storage properties. Now we're going to move on into aquifer tests, and I'll do a little intro here. I should mention that we're going to do 3 specific aquifer tests, kind of simple versions of it. There's more than that in the textbook, and also there is software available to do these aquifer tests. We're just going to do it in kind of by hand calculations and a little bit in Excel. Probably the most popular software for doing these tests is Octosolve. You can see it has a whole bunch of different tests, different variations of the test. We're just going to do the simplest version of each of 3 tests, but those tools are there if you want them. The Groundwater project, which is where we get our text, also has a text on some of the basic methods for aquifer tests. So we're going to solve the transient well equation. If you'll remember the transient well equation, which looked like this, we had the head as a function of the radial distance from the well and as a function of time, and the 2 parameters that affect that are the transmissivity and the storativity. We'll go through a method based on the Theis solution to it. Charles Theis was a hydrologist, and he many years ago, almost 100 years ago now, came up with a solution for this, and it produces a characteristic equation and characteristic plot of drawdown versus time. So he set it up that the drawdown, little s, is equal to the flow rate over 4 pi times the transmissivity times the W of u, where W of u is a function with this integral in it. So he solved that numerically, and you can actually solve by an infinite series, where u equals the parameter r squared s over 4 big T little t. So we have W as a function of u, and you can look up tables for that in a solution. I actually have it in Excel. There's an infinite series to it. And it turns out to look like this, that W versus U has this curve, or W of U versus 1 over U has the one that goes up like that. And actually, if you plot, I'm getting ahead of things a little bit, well, I'll just say it right here, down here. The W of U versus 1 over U graph, you can see it there, matches a drawdown versus time graph. So the method, we take the drawdown versus time, we match it up with a plot of W of U versus 1 over U, and with that match, we can come up with the parameters. All right, so first method we're going to do again is the Theis Curve-Matching method. This is laid out in the text. What we do is we obtain a Theis equilibrium type curve graph. Now, in the olden days, they did this with paper. They printed this out in a blank. This is copied and pasted from the text, blank log graph. And a little aside here, when I first did this for a living, I just got my PhD, and I was all up to speed with modeling and coding and everything like that. And I thought, well, I'll just write a code for this. And the first one I did, there was another guy, an older engineer in the firm. He did it with physical pieces of paper, and I did it with wrote code to match the data to the function. Anyway, we came up with the same solution, with the same numbers. So you have a blank log graph, and you plot your data on that, and then you compare it to the Theis equilibrium type curve. And again, you can do this in Excel. I have it set up in Excel or with software like Octosolve. So we plot that versus radius r on a blank log graph. An example is shown in figure 45a, which I pulled from the text. Notice that you have to have a couple things here. The axes must be parallel, and the squares in both the graphs must be the same size. Now, if you're using the paper, this is already set for you. You do need to make sure you don't you have them parallel. So he points out in the text, when you move the paper around, you got to keep those axes parallel. You can't slant them to fit because it won't work that way. So we match up our data to the data plot of drawdown versus time against the W of U versus 1 over U graph, and we find how that matches. Now, once it matches, we can just find one point on our graph. On paper days, you just take a pin and put a hole in it, and you have that match point. It does not have to be on this curve. It can be anywhere in here as long as it's lined up. So this is a figure from the text, and this is actually also in the numbers. We have you calculate that in the homework, and then I also ask you to try another point on there and see if you get the same answer. So I choose this point here in his example. He has 1 over U equals 3.2 and U equals 0.31. So U 0.1, 0.2, 0.3. 1 over U is 0.1, 1, 2, 3, 3.2. And then the double of U is about 7, and the drawdown is about, well, right at 1. We put it on that there. So we match up those points, and then we plug our numbers into, we have the flow rate. We pulled our W of U off our match point. We have the drawdown we pulled off of that match point too. So we calculate the transmissivity with that. And then to calculate the storativity, we also use our points. Now that we have our T, we plug our T down into here. We have our T off of our graph. We have our measured R squared, our U off of our graph, and then that calculates the storativity. So let me do a little example here. I actually have this. I'll pull up the Excel I have for this. So I have W of U versus U in Excel, and I plotted it up here, and then I have a plot of data from a pump test, and again on a log-log scale, and I have these lined up in so they have the exact same size. Again, if you're using physical paper, you don't have to worry about that because the paper is the same size. And if you're using Octasol, you don't have to worry about that. So I come over and I try to match these up. So this matches the early, that's the early time stuff. The early time stuff, you often have a little funky stuff happening. So I'll go maybe about there. That's a pretty good fit. So I take that and then I find a point in anywhere in here. It can be up in the corner, down in the corner, it could be along this graph. I usually pick a convenient point that has the whole numbers there. Returning to your notes, this is example. So this is data I have. Q is 4 gallons per minute. I think this is one from our underground storage tank sites that I pulled off. So this is our data plotted on a log-log scale, and then I matched it to the U versus W of U. So I put the drawdown versus time in red and the W of U versus 1 over U in black. So to make it easier to see, I'll probably do the same thing in if I give you an exam, make those different colors so it's a little easier to see. So I'm going to choose a match point anywhere on there. And I'm going to choose where drawdown is 0.1 and T is 10. And then W of U there also equals 1.0. Those happen to line up. And then 1 over U equals a little tiny bit less than 0.5, right? I'm going to say 0.48. So I calculate T from T equals Q over 4 pi S W of U. I have Q equals, looking over here, it's 4 gallons per minute. I convert units later here, over 4 times pi times the drawdown from my match point is 0.1 feet, that does have units, times W of U, which does not have units, is 1.0, and that equals 3.18 gallons per minute per foot, and that translates out to 0.071 cubic feet per second, or 0.43 cubic feet per minute. Now that I have that, I can then calculate my storativity equals 4 times the T, which now is, I'll do the time I have in 10 minutes. So I'm going to do 0.43 feet cubed per minute times 10 minutes times a U from our match point, and our 1 over U was 0.48. So your U is going to be 1 over 0.48. That's dimensionless. All over R squared, and I have R is 30 feet squared. I have feet cubed goes down to that, feet squared. I have minutes. I have minutes cancel out, and S equals, wait, this was feet squared. Yeah, always check units. That was feet squared. So it does cancel out. And that equals should be dimensionless, 0.039. So what we said before up above, we said if S is 10 to the minus 3 or lower, it's confined. If it's 10 to the minus 2 or higher, it's unconfined. So this looks like it might be an unconfined aquifer, and that would make sense if this was one of our underground storage tank sites. And Octosolve has this method and variations on it. You put your information in there, fully penetrating. We'll talk about that with the slug test, and plots up your data. And then you can just actually press a button to have it match. And if you aren't happy how it does that, which you might not, because you might see here again, you might have different parts of this that are a little different, and you want to kind of override that and match a certain part. You can do a visual match of your own. The Theis Curve-Matching method is really for confined aquifers. For unconfined, you have a little different thing happening. You have these different zones, and this caption explains it. At first, you have the water coming out near the well, and then you have it drawing down, and then when it starts to draw down more, because the water table is lower, you reduce the transmissivity, or hydraulic conductivity. So you have that funny curve to it. And actually, if you look at the front page of the Octosolve thing, it looks like their example they're using in there for the pumping test. That looks like an unconfined aquifer to me. So there are methods for doing that, and again, Octosolve can do that. These, by the way, are copied from the text. There also, you can adjust for if you have a leaky confined aquifer. Remember, if you have one of our layers above or below your aquifer that actually lets some water through, not a lot, but it will be dashes without the boundary. If it's leaky, you'll get the more flow out without as much drawdown. Whereas if you have a boundary that you're hitting, now you're going to have to draw down more because you're not getting water from past the boundary. So you'll have a little more than the basic equation tells you. And we have ways to adjust for that. So that is the Theis Curve-Matching method.